Okay, good morning. I won't keep you too far from lunch, but so my perspective is more of a systems level perspective, I think, and looking at considering the different techniques that are available and the different systems that are planned to integrate together. How can we create more cognitive opportunities in the architecture? So today I'll just talk a little bit about some of the challenges I've seen and heard about traveling around at different conferences, and then also some of the protocols that we've been working together on in my lab in terms of trying to bring adaptive and cognitive processes to common networking problems. So I guess I just went over this. Some of the specific problems we'll look at is, of course, cognitive radio, and how you can be more adaptive in your approach to packet transmission or selecting available channels. And then also an 802.11 example with ultra-wideband in adaptively changing the transmission energy that you use to send a signal from one place to the next. And then I'll mention some applications that we're working on here with a couple of other students. So the networks that I originally started working on were very low capable networks with minimal electronics on them, wireless sensor networks, distributed topologies, where you have lots of nodes and tens to hundreds to thousands, and limited capability in terms of the device itself, but you might have access to a more capable sink or base station or laptop in the environment that can provide more processing and services. So how can you take advantage of dense deployments and close proximity using ad hoc protocols to create more opportunities for transmission or coordination among networks? More recently, this wireless sensor networks idea has expanded to many different types of devices and different types of networks under this umbrella of IoT. So IoT doesn't necessarily mean a sensor, but it could be a router, it could be other devices that are much more capable but are trying to operate on a more private or local environment. So looking at the web stack, I'm used to walking, I'll stand still. Looking at the normal web stack, we have a standard grouping of protocols that are commonly used in systems, from 802.11 that we use for Wi-Fi, and then the standard IP version, either 4 or 6, and IPsec that goes along with it. And its assumptions of stability, relative stability, and not too fast mobility. You can move around with mobile IP, but the assumption is you have some tethering point to the network. With TCP and UDP, again, you assume that there's a steady process that's followed, a steady policy for TCP bucket size and segment size that revolves around the round trip time and increasing according to the congestion in the network. With wireless networks, we evolved TCP a bit to say, you know, there are times when the round trip time fails because someone may turn a corner and get dropped from a connection, but 2 seconds later they're able to receive the connection. So TCP in itself, its original form, will drop the bandwidth to prevent clogging the network, but there need to be updates to TCP to allow for this irregular round trip time with wireless networks. So you can look at TCP Reno or TCP Westwood. There are lots of different flavors of this TCP to handle this problem. And then at the application layer, this is running on top of sort of a capable system that has processing power and the ability to hold heavy apps that can do security, user-defined applications, and other things that are readily able to handle most applications that users want to operate. So by contrast, in the Internet of Things stack, you have at the MAC layer and the physical layer a couple of different options. In this case, I show only the Zigbee option, but in the next slide you'll see you can have a wide variety of options here at the physical layer and the network layer that people in your, or devices in your network will have an entree into your backbone system. At the internet layer, we have a lightweight 6-low PAN to encompass some of the IP version 6 functions, but not enough to wear out the battery power or require a processor or a router to be involved in the network. At the transport layer, DTLS and UDP are most often employed for that same reason, processing, and you don't really need all of the TCP end-to-end guarantees that you would need for cellular network, for example. And we're continually seeing new developments at the application level like CoAP and MQTT for manufacturing, and other applications for just having a device that's simply reporting little text blips or little messages that some sink somewhere is recording data from and telling the network to respond to that. So this stack is a bit different from the original stack in that it has options, it has flexibility, it has varying capabilities for the nodes, but they're expected to all be able to communicate in the same system. So here's an example of the variety here at the lower layer of the protocols, where you can run anything from Zigbee to Wi-Fi. LTE has cellular, MAC and physical layer, but it also has LTE Direct, which is more like Bluetooth. And coming up is the LTE narrowband, which is supposed to be a precursor to an IoT-enabled system in the LTE network as well. The power line communications is also an option for IoT networks, where you have these very simple protocols for devices plugged in and reporting information. So feel free to ask questions and jump in if you want to. So at the network layer, again, you have this variety of how you want to go depending on how your network is designed. And on top, you have some IoT-based application. So this stack is the MQTT version, or machine-to-machine version for the protocol stack, where you see the multiple nodes and the pathway from the node itself to a gateway and then to a router. So here, again, on the local network, it's very simple, very lightweight protocols with Bluetooth or Zigbee or some other ad hoc routing. At the gateway, you have a chance to convert protocols to either a cellular network to access the outside world, or maybe a Wi-Fi or more enabled network. But the idea is to take all of this variety and bring it under one unified umbrella. And for our interest is to make this system a little bit more automated in figuring out what kinds of devices are present, what's needed, and how do these devices need to behave. So this cognitive network idea is often interpreted as cognitive radio by others, but it's taking it to one larger abstraction, and that's the idea of having a network that's local and able to function in many different scenarios, especially considering the variety of devices that are there, and to have some way of inserting policy based on what's happening in the network, whether the devices are being used simply to report security information, or they're being used by human beings to view images or engage in applications or engage with other people, or the devices are simply passively observing a temperature and reporting it every 30 seconds. So if we can figure out what devices are available and how they're being used, then the protocols they're using can be adapted to whatever they're engaging in at the moment. Whether they need to access a sink or a tower or just the station sitting next to them can also be adapted. So on this local network, can we have some way to insert policy? Can we have some way to allow the decision to be made at that local network to cause the devices to behave differently? You can also think of this as cognition happening in the device itself, where it's observing how it's being used and then adapting the protocols according to how the user is intending to operate the device. So a couple of examples where we use this thought process in exploring some protocols in our lab. We looked at radio dynamic spectrum access, where you have a primary user and secondary user accessing the same channel, and hopefully I have a diagram of that. And how can we approach jumping into the channel, not just from the perspective is there bandwidth, but also is this a good choice according to the specifications of my particular device. And then, if I'm going to send information, should I just send information as specified by the network, or should I change that according to what my device will experience after I've transmitted it? So our motivation is to take these traditional cognitive networks, where you mostly look at throughput and delay, and then update them for, in our case, we looked at the constraint of energy. So if you have these small devices, can they use cognitive networking or cognitive radio techniques and still be able to maximize their energy consumption? So our network model is probably familiar to all of you. We have a base station or a tower in the middle that's collecting information from these sync stations, and we have nodes that are more capable in the network that are able to be cluster heads, and nodes that are devices that are passively being used either by this monitoring system or being sensors, or some users not using their cell phone, they're just a participant in a security protocol that's going on in the network. The primary users are the more capable users that have some licensed reason to be using that bandwidth. And as you know, the secondary users are not licensed to be there, but can occupy the bandwidth when it's available. So the idea is, when we have this slotted structure of packets and the users have opportunities to transmit in the packet, can we estimate when it would be advantageous for the secondary device to transmit in the channel? So usually we're focusing on the primary device and how it can not be interfered with, but in this case, how can the secondary device make a better choice of whether to transmit or not? So I don't know if you can see this. It says current residual energy location information. So we take some estimate from the device as to how much energy is left in the system, and we incorporate that into some decision process. This cluster member in default mode remains asleep unless it's collecting data. It has some trigger to tell it that it needs to use the system to report, or the user is actually starting to send. Then it first sends some request packet to the cluster head in order to figure out if it's best to transmit during this session. The request packet contains this location information of the sensor itself, as well as its residual energy available on the device to be input to the decision process. So the cluster head, having this information for all of its devices in the cluster, can accept or deny this request. If it's accepted, then the data is sent. If it's sent, then we go into the cognitive radio process of looking to see if there's a primary user in the channel. And if there is a primary user, then we go back to either the sleep mode or some waiting time period, a back off period, and start the process again. If the primary user is not present, then we proceed forward with the process of jumping into the channel. So this idea of looking at the residual energy, we examined a little bit to see are there opportunities where we can change the way we transmit in order to have more energy left after we've engaged in this transmission. So we looked at the expected energy consumption based on the packet length that we would send into the channel. So we can either look at the available number of slots and just say, I'm going to send enough information to fill these slots. But it could be that we don't need to send that information, or it could be our energy is such that we'll have to send some subset of the information and try again for the next cycle. So we looked at the expected length of that expected energy consumption based on the length of the packet and based on whether we will be able to be successful in this transmission or experience some collision. After we get the energy expected, we include that with some coefficient we called residual energy coefficient, RC, for a particular user or a particular channel, and come up with this coefficient for each user that's a secondary user trying to get into a particular channel. So once we have this coefficient, we can try various different channel assignment schemes. For this presentation, we just picked out 3: a random pairing, greedy search, or optimization based. Just by definition, we have active sensors, we have sleeping sensors, and we have a certain number of available channels. So in the random pairing approach, this is a PowerPoint slide that had some animation, and now I converted to PDF, so you see all this at the same time. That's okay, I can point it out. So we have active sensors here, and we'd pick out each sensor, and then with each sensor, we pick out an available channel, and then when we have a matching, then you'd see that it's done. In this case, if we use a greedy search, we'd pick out the best search for each user as it comes along. So this sensor is the first to pick out a channel. It has calculated these R coefficients for each channel for that particular user. It turns out that this, for the residual energy left, the probability of success in that particular channel is high for channel 4. For the second user, or once this channel 4 is taken, this, you can imagine this column and this row is removed from the matrix. Then for the second user, they do the same thing. The highest R coefficient for the available channels left, which would be these 3, would be the first channel. And now this row and this column are removed. And then out of the final 2 channels that are left in the system, the sensor number 3 takes this channel, and they're assigned that way. In the third case, we do an optimization-based assignment based on both the residual energy of the user, but trying to maximize the energy for all of the users in the network. Yes?
So you assume that there is some global coordinator who's doing this? It means it's not done in a distributed fashion by each sensor?
So in this case, there is a cluster head that's taking the information that's collected from the sensors and then returning some schedule. But we can, well, it would take some additional research, but I can see where it could be a distributed basis if the users were to exchange some information. Then we'd have to optimize the power expense versus the exchanging of the distributed information or using the cluster head.
So is there also any connection between this problem and the multi-arm map problem? You could potentially sort of, each sensor could probe channels over time and try to figure out which channel are less likely to be used by a primary user.
Yes, we do have some of that. I don't think that's shown here, but there is some, except for we didn't do it with the multi-arm. We did it with a single channel, just observing a channel to see if it is a good candidate or not a good candidate. But we looked at it from one device's perspective, and that would be a good extension to share the information among different devices. Any other questions, comments? Okay. So over this optimization, we have the ability to benefit the entire cluster instead of a particular user. So we optimize based on the number of channels that are available and also the number of sensors that are active and have some intention of transmitting information. So in this case, we have a different set of channels that are selected. The purple ones were the original selection. In this case, the channel sensor 2 gets a different channel, sensor 1 gets a different channel, but sensor 3 gets the same. But the idea is, considered as a whole, all of the sensors have the most possible residual information, residual energy left after the packet will be sent. So just comparing the different algorithms, we ran simulations for these three over various numbers of sensors in a network, and observed what we expected, that using this optimization technique, we ended up with a better, more prolonged lifetime for the sensors. And, but the greedy and random approach didn't present too much of a difference in our results. So the next thing we looked at was a packet size adaptation, which looked at the energy waste by sending packets that may not fit in the channel or may be longer than needed for the energy that we have left. So if we increase the packet size, then we have a higher probability that the primary user jumps back in and collides. If we decrease the packet size, then we have expended a lot of energy not to send very much information. So our goal is, again, to improve or design according to the energy factor. So here we looked again at this energy consumed in a control slot and versus the energy consumed in a data transmission slot, given the amplification, the distance, and the bits, number of bits you have in these packets. And then considered the amount of successfully transmitted data you would get given the probability of having this packet being successful at this bandwidth with this packet length for this particular user or slot duration. So given all this information, we figure out the energy per bit expended to send packets in this network based on these factors above. If we can minimize this energy per bit over this packet size, then we can maybe optimize the number of packet bits that should be sent per packet under these particular conditions. So looking at these initial results, we had an ability to minimize this network energy that's being expended based on a fixed packet size. But when we use the approach of adapting the packet size according to various factors of the network, we can stabilize this value a lot more and at a low value by being adaptive. And again, considering the control traffic and other things that we had to incorporate into the energy, it's still a benefit to use this approach. So on this slide, it shows the number of transmitted information bits. And adaptive can sometimes give us a benefit of even more bits than we would expect would be beneficial, depending on what the conditions are of the network. So the other adaptation we looked at for these small, closely located ad hoc systems was to look at some of the existing protocols that we use that maybe can be updated to consider environmental information and behave differently just in its normal operation, adjusting different parameters. So this one is for, again, for an ad hoc network for small devices that operate using ultra-wideband. And we looked at the problem of pulse position modulation, where you receive a pulse in a given transmission window and you declare whether it's a 0 or 1 based on its position. So it's a very simple scheme, low complexity. How can we adapt that to what we might want to do in the environment? The operation of the scheme is to take a transmitted signal 1 or 0 and label it so by the pulse's position. So pulse transmitted in this first window received would be labeled as a 0, for example, and a pulse transmitted in the second window would be labeled as a 1. So each bit that's transmitted takes up this 2 TW, or this transmission window, for that one data bit. If we assume we don't have any noise, then the received signal will have a nice characteristic for the power spectrum for the integration window, and the receiver will get a clear signal of what bit has been sent. But in practice, and here we just added a WG in, we have some energy in both of the windows, and we have some spread, and we end up with the problem of detecting in which window was the intended bit transmitted and which is mostly noise. So we come up with a decision-making scheme to decide whether the bit was originally sent in this window or that window since this is not very high in processing and just pulse position modulation, most of the time the guess is just whichever window has the most energy. So what we looked at was characterizing this window a bit more specifically and looking at the actual energy per bit for the window and a scaling factor for that window depending on how much time we might allot to gather the information. If we had all the time in the world, what would the energy per bit look like? If we take a varying view at that transmission window or integration window, then how good is good enough to make the size of that window? So looking at the probability of bit error based on adding this new factor that scales the energy for the given integration window versus an open case where you have all the time in the world, we came up with this probability of error for each bit. And given the bit error, we came up with a signal-to-noise ratio expression. This is the original expression for the energy per bit over the noise density, and then we incorporated this energy scaling factor. What we're looking for is this minimal number of, or minimal amount of signal energy needed to send the same number of bits. So our optimal integration time is not able to solve, we're not able to solve explicitly, so we just use the exponential fit to estimate it and come up with this idea of this optimal integration window for the bits. Yes?
What's your time spread here?
Time spread.
That's the order of time spread, right? So you might be running in, because usually the problem with PPM is you get hit by multipath.
Right, right. So the time spread, I think, was taken from one of the standards, I can't remember which one, but the IEEE 802.11 standard was the one that we used. Okay. But I don't remember what the value of it was right now. And I can provide the links to the papers to show you. Yeah. So here for, in this slide, we consider the optimal integration time, considering only the fact that we're changing this integration window and we've been sent a pulse and receive it with white noise, or just send a pulse and receive it and change the window. And here we consider some noise factors. Okay, so that was
SI time spread, the physical time spread, not the receiver phase law loop.
Right, right, yeah. Okay, okay. I thought you meant that. Okay, good, good. So here we have the symbol interference and the frame interference. So by symbol, we just mean if you send a bit in this first frame, then there's another bit following in the next frame. Is there any interference between the two? In the second case, we look at, is there any interference within the frame itself from the second phase that's supposed to have no activity and the first phase that has the bit in it. We took an expression for this interference based on both ISI and interframe interference to come up with a more realistic version of our integration time estimation. So having this signal energy or signal to noise ratio, our bit error rate, gives us our integration time, optimal integration time based on interference from the frame, interference from the symbol, and then also just white Gaussian noise. We simulated this system using MATLAB and did some analysis using our theoretical basis, and we're able to discover that, yes, you can make a significant difference in considering this integration window time versus how much you're going to transmit a particular bit in terms of a given protocol that you'll see in the next slide. So here we see an improvement of between no interference and having ISI and IFI, you can have a significant difference in your energy, bit energy per noise density. The CM1 to CM4 are those IEEE standards for different equipment and different channel models. So here, just to bring you back to this slide, we're looking at the idea of transmitting energy in one slot and no energy in the next slot, and trying to come up with some expression of where was the most energy. In the presence of noise, we have the difference of these two windows. Now, since we've have a way to change or estimate what size window will give us the best representation of the SNR, then we have a more likely ability to interpret that window as a bit or no bit. So this just gives an example of how it works after several iterations. The number of bits will give you, obviously, a better fit according to the ideal case of no interference or just simple Gaussian interference instead of frame and symbol. How we've applied it is to incorporate it into a MAC protocol. So something like 802.11 is a protocol sent over wireless networks that you all probably know, where you send a control packet, RTS, and receive a control packet, CTS, before sending data. So the norm is to have RTS packet sent over a given data rate for the channel at a given size over this given transmission time. If we add this adaptive approach to it, we can use the RTS and CTS as training sequences for this integration window time. So in this case, sending just RTS, CTS data ACK in a timing diagram amounts to this data exchange. But instead of sending this the same way every time, maybe observe what's happening in the channel first with each RTS, CTS exchange. So once the RTS is transmitted, then node B can observe the behavior of this RTS and use that information to detect channel information and estimate the energy scaling factor from what's been received in the RTS, since most of the RTS packets all look the same except for the address. Oops. So once this scaling factor is determined, B can determine the optimal integration time for that channel and return the CTS with the new data rate. And now CTS at A can set a new data rate based on the information from B, and they can transmit at this, I won't say optimal data rate, but more beneficial data rate for this one communication at this one time. Then after the communication is over, you can reset the data rate and go back to the nominal standard. So the benefits for this particular case study is to have an optimal integration time, consider interference, and then create a more adaptive approach to networking instead of using the same process every time. So I'll just sum up this way. I know we're heading towards lunch. So the application that we're trying to apply this to is there's a student, Tiago Borba, in agricultural engineering, and his application is to set up these sensors in fields, in his case strawberry fields and potato fields, and try to detect things like leaf moisture, weather, rainfall, etc. But they're out in the environment and they're in a densely distributed through brush and other things. They have to make their way back to either a sink at a farmer's location, or a farmer will drive through in a truck and collect data as he goes by. So we're setting up these sensors now with Zigbee and some with Bluetooth, and trying to run some of these protocols and see how they turn out in the environment. So that's, I think, all I've discussed. In summary, the idea of cognitive networks is to relax some of these fixed standards and the way you do things the same way every time with the same devices, and then let the device choose how it wants to transmit, how long, how often. That's it. Any questions? Yes.
So you picked PPM, but it's not going back to the first part. You know, if you're doing something cognitive, and one of the problems with PPM is you're using all of the bandwidth at all times.
Yes.
Have you thought maybe of using impulsive frequency shifting, because A, it's capacity achieving in the wideband regime,
right?
Versus PPM. B, you don't have to worry about the multipath time spread, you know, I
Okay.
assign between. And the other thing is then, given the first part of your talk, you also don't really care who else is communicating because you can just kind of block out, naturally filter out those portions of the frequency where it's very, very hard to do a ppm notch filter.
Okay, yeah, I can consider that. Yeah, this is our first work on that, but that would be a great idea, yeah.
With sort of, you know, the wideband aspect
Mm-hmm.
and the
Adaptive,
channelization
yeah.
aspect, if you will.
Okay. Okay, that'd be a great idea. Thanks.
Okay, well, thank you.
Thank you.
So, the last
So-
speaker, keep it us for lunch.